calculus. Separable differential equations. Okay, that's quite enough of that. All right, so today we're going to be not just finding an approximation to the solution of a differential equation, but we're actually going to be solving differential equations for the very first time. Okay, so here is your basic differential equation. dy dx equals some function of y times some function of x. Now, we're trying to separate the y's and the x's. Now, what it looks like is we're going to divide both sides by f of y and multiply both sides by dx. The thing is, like we said before, dx really is not a defined quantity, so that's really not what we're doing. What we're doing is we're taking the integral of both sides. So what we have here is the integral of dy over f of y equals the integral of g of x dx. Okay, so now when we integrate this, we know that the integral of 1 over f of y is going to be natural log f of y. And then the integral of g of x is going to be g of x plus c. And then we proceed to simplify that. Okay, so this is general information. Let's try a specific problem. So okay, we'll check out example 1. dy dx equals x squared over y squared. So, like we did before, we're just going to get the y's on one side, the x's on the other. So, what I'm going to have is the integral of y squared dy equals the integral of x squared dx. So this means I have y cubed over 3 equals x cubed over 3 plus c. Now notice we don't put plus c on both sides. The convention is we just put it on one side because the constant is a random constant. So if we put it on just one side, then it counts for both of them. So now I can solve for y. So what I do is I multiply both sides by 3. So y cubed equals x cubed plus c over 3, which is just another constant. And then we say y equals the cube root of x cubed plus c over 3. And now, next step is they give us initial conditions. So they say y of 0 equals 2. Now remember what that does. This is an entire family of solutions depending on what c is. If you give us one single point, then we can get one single solution because c will be a strictly defined quantity. So what we're going to do is if y of 0 equals 2, that means x equals 0 when y equals 2. So we're going to plug that in here. So 0 equals, oops, rats. Two equals the cube root of 0 cubed plus c over 3. So we'll just cube both sides, so c over 3 equals 8, and c equals 24. Okay, so now I can just say y equals the cube root of x cubed plus 24 over 3, which is 8. So now here is the specific solution for these initial conditions. That's it, piece of cake. Okay. Let's check out example 2. dy dx equals 6x squared over 2y plus cosine y. Six x squared, right. All right, same thing. We just get the y's on one side, and the x's on the other. So now I do this integration, and that's going to give me 2y squared over 2, which is just y squared. Integral of cosine is sine. And over here we have 6x cubed over 3. So 2x cubed plus c. Now, did they give us okay, yeah, they didn't give us initial conditions, and it's impossible to get y by itself. We can't factor out a y or anything. So basically, this is your solution, and you could graph this for any random constant. Okay, so let's try example 3. Y prime equals x squared y. Yeah, let's just get rid of this. Y prime equals x squared y. Now, clearly y prime is dy dx. So we're going to get the x's on one side, the y's on the other. So dy over y equals x squared dx. Now we need to take the, oops, forgot the integral. Never forget the integral. And that's just too ugly. Because dx without an integral is meaningless. Okay, so now the integral of dy over y is natural log absolute value of y equals x cubed over 3 plus c. Okay, now we can get y by itself. If you remember from algebra 2, how do you undo log? You raise both sides to the power of e. So we have e to the natural log absolute value of y equals e to the x cubed over 3 plus c. So e to the log, that's just absolute value of y. And this, what I can do is break it down into e to the x cubed over 3 times e to the c. Now, what we do, e to the c is just another random constant. So what I'm going to do is I'm going to say let a equal plus or minus e to the c. Plus or minus allows me to get rid of the absolute value. So now what I end up with is y equals a times e to the x cubed over 3. Now, that is my general solution for any values of a. And so that's a family of solutions once again. Okay, so they give us initial conditions. Okay, no, they didn't give us initial conditions, but let's say they did give us initial conditions. Let's say they told us that y of 0 equals 5. Okay, so that means when x is 0, y is 5. So 5 equals a e to the 0 cubed over 3, which means a e to the 0, well, that's just a times 1, so that tells you a equals 5. Okay, so that says then that the specific solution is y equals 5e to the x cubed over 3 at the point 0, 5. There's my specific solution to that differential equation. Okay, so once again, piece of cake. It's just too easy. So we're going to have to crank up the juice a couple of notches. This problem that we're about to do is maximum juice. Check out example 6 on page 606. Okay, we've got a tank that contains 20 kilograms of salt dissolved in 5,000 liters of water. Of course, this is in France. Brine is basically salt water. Brine that contains 0.03 kilograms of salt per liter of water enters the tank at a rate of 25 liters per minute. The solution is kept thoroughly mixed and drains from the tank at the same rate. How much salt remains in the tank after a half an hour? Okay, so first thing we need to do, when I first taught you word problems, the very first thing we do is define the variable. And this is super important in a problem like this. Okay, so let's just write down what they gave us. So we've got 20 kilograms of salt in 5,000 liters of water. Okay, then we've got 0.03 of a kilogram per liter entering. Let's go. Let's be a little more specific here. 0.3 of a kilogram of salt per liter of water enters at 25 liters per minute. Okay, then we've got 25 liters per minute draining. Now, the salt coming in is exactly 0.03 kilograms of salt per liter of water. But the salt going out is going to be constantly changing because it's whatever the concentration of salt in the tank is, which will be homogeneous or homogeneous, is going to be leaving at 25 liters per minute. Okay, so the question is how much salt is going to be present in a half an hour or 30 minutes. Now remember, defining the variable is answering the question with the variable. So we say m equals the mass of salt at any time t. So those are our two variables. And we're given initial conditions that there are 20 kilograms of salt. Oh, you know what? Let's say mass of salt in kilograms at any time t in minutes. Yeah, that's important too. All right, so we've got the initial condition, 20 kilograms of salt are present in the water initially. So that means m of 0 equals 20. So the mass at 0 time is 20 kilograms. And what we want is the mass at 30 minutes. Okay, now let's do one more thing while we're defining variables. dm dt is the rate of change of mass with respect to time. Hey, I'm recording right now. Okay, dm dt is the rate of change of mass with respect to time. So that's going to be measured in kilograms per minute. Probably going to be about 10 more minutes. Can
Okay.
you? Why don't you just hang in here and just keep working, and
Okay.
I'll get to you as soon as I finish this. Okay, is that camera still on?
Yeah.
Okay, that's good, because it was a tragic situation when I was talking to no one.
Oh.
And it was the best math lesson in the history of mathematics instruction, and it was gone. Okay, so we know that dm dt is the rate of change of mass with respect to time, and that's going to be measured in kilograms per minute. So now, the total volume of fluid in the tank is 5,000 liters. So that's going to be constant. All right, so first thing we're going to do is the mass of salt out. Yeah, let's put this in red. Mass of salt out. Okay, that's going to be, no, I'm sorry, let's do mass of salt in first. It's going to be easier. Mass of salt in is our 0.3 kilograms of salt per liter of water, or 0.03 kilograms per liter, times 25 liters per minute. Okay, so liters cancel, now I have kilograms per minute. And so that's going to be 0.03 times 25, which is 0.075 or 0.75 kilograms per minute. So salt is coming into the tank at 0.75 kilograms per minute. Now, the mass of salt out that's going to equal m kilograms per 5,000 liters times 25 liters per minute. So, are you actually ready to take the test right now?
No, I'm just going to take it after school, right?
Okay, all right. Yeah, I just wanted to make sure. Okay, so m kilograms per 5,000 liters, that's how much water is in the tank, and you've got a certain number of kilograms of salt that's unknown. M is the mass of salt at any time, so it's a changing mass of salt, but the 5,000 liters of water never changes, and the rate that the solution is leaving the tank never changes either. So that's kind of handy. So now notice the liters cancel and we're left with kilograms per minute. So we've got 25 over 5,000, which is basically 1 over 200. So we've got 1 kilogram per 200 liters. No, I'm sorry, it's not 1 kilogram, it's m kilograms per 200 liters. M kilograms per 200 liters out. Okay, so now, the next thing we realize is that mass in equals mass out. So what I can say is, mass in equals mass out. So that means, well, let's just, yeah, let's do it like this. Mass in minus mass out equals 0. So the mass in is 0.75 kilograms per minute, and this really is dm dt. Because what we're saying is the rate of change of mass of salt with respect to time never changes. And that's going to be the mass in minus the mass out is going to be the change in mass with respect to time. Okay, so that means we have dm dt equals 0.75 minus m over 200, which equals 0. Okay, so now all we do is get common denominators here. So basically this is going to equal 150. See, I multiplied both of these, we'll multiply the top and bottom by 200, so this is going to be 150 over 200 minus m over 200, which equals 0. So 0.75 is 150 over 200. Okay. So now this means we've got 150 minus m over 200 equals 0, but it also equals dm dt. Okay. In case you hadn't noticed, we have a differential equation here. Notice we have the derivative of mass with respect to time, and we have mass itself, both in the same equation. So, what that means is, it's time to solve a differential equation. Okay, so let's give that a shot. So, on to the next board. dm dt equals 150 minus m over 200. Now, this is a challenge here, that it took us all this work just to come up with the differential equation, and now we're actually ready to get started. And the other thing I want to let you know about this is, if this looks really fun to you, then you should be a chemical engineer, because this is the kind of crap we did. Okay, so cruising onward. dmdt 150 minus m over 200. So we need to separate this thing. So we're going to bring the m's down to the left. So I've got the integral of dm over 150 minus m equals the integral of dt over 200. Okay, so now when we do this integration, we have natural log absolute value 150 minus m equals t over 200 plus our arbitrary constant. Now, let's not mess around with this constant any more than we have to. Let's turn it into a number. So how do we get a number for the arbitrary constant? Yeah, right. Okay. We plug in the initial conditions. The initial conditions is the mass at time 0 was 20 kilograms. All right. It is actually 20. There's a 20 there, you just can't see it. All right. Okay, so now what we do is plug in 0 for t and 20 for m. So natural log of 150 minus 20 equals 0 over 200 plus c. So clearly c equals natural log 130. And so I can go back up to my solution here and say natural log absolute value 150 minus m has to equal t over 200 plus natural log 130. Okay, so I messed up. Okay. Oh no, I was writing in pen. Okay, so notice when we took this integral, you have a minus m here. So this has to be the negative natural log of 150. And this is negative natural log 150. So c actually equals the negative natural log of 130. All right. So now we're happy. So the negative natural log 150 minus m is going to equal t over 200 minus natural log 130. Okay, so next thing we do is let's just multiply both sides by -1, get rid of that pesky negative that I forgot in the first place. So natural log of 150 minus m is going to equal natural log of 130 minus t over 200. Okay, now we got to get rid of the natural log, so we take both sides to the power of e, and so we're going to end up with 150, absolute value of 150 minus m is going to equal e to the natural log 130 minus t over 200. Okay, so let's clean this up now. So that means we're going to say absolute value of 150 minus m equals e to the natural log 130 times e to the negative t over 200. Now, e to the natural log 130 is clearly just 130. So we've got absolute value of 150 minus m equals 130 130 e to the negative t over 100. Okay, so now the next thing we say is that, well, there's two ways of seeing this. We know that the mass can never be more than 150. But the other thing we know is 130 times e to anything has to be positive. So we don't need an absolute value here. We can just say 150 minus m equals 130 times e to the negative t over 100. Because, like I said, there's no way e to anything could ever be negative. So there we have it. Now that gives us that mass equals 150 minus 130. This is obnoxious. (130) e to the negative t over 100. Okay, now the last thing we have to do is we want the mass at 30 minutes. So all we do is plug in 30 for t. So 150 minus 130 e to the negative 30 over 100, or negative 3/10. And how the heck did that turn into 100? You guys need to let me know these things before I screw up. Yeah, I have no idea how I did that. Okay, so this is negative t over 200. So 30 over 200 is 3 over 20. This is, let's see, that's 0.15. Okay, so now we crank that out and we get that the mass is going to equal 38.1. So that means we go back to the initial question. How much salt in the tank after 30 minutes? And that's going to be, oh, rat's wrong color. 38.1 kilograms of salt in 30 minutes. That's it. Piece of cake. Okay, have fun with these.